All right. Yes. So, virtual students, I just spent like 15 minutes of class trying to find all the equipment for getting like the carts and the air track set up so that we could maybe collect actual data, and we got everything but the box to get data from the sensor into the computer. So, alas, it was all for nothing. Although at least I know what we need yet. So, where did we leave off last class? What did we end on? It was only 2 days ago. Nobody remembers what we did? Ethan, you weren't here? Ah, dang.
Was it one of the papers? I remember, was it a couple papers? But I don't remember which one we finished.
Ethan, what's the last one you did? Wasn't it the front side of 1E?
Last time he was here, we were talking about the Kennedy truck.
The relative stuff?
The Kennedy truck.
Oh, that's right. So we finished the relative velocity one, which Ethan, I think you should have. Let me get those for you. I'll get you those. Ethan, they should be pretty straightforward. So yeah, we finished E, which was the relative velocity. Then we looked at constant velocity, but a velocity time graph. And then we did another velocity time graph, but the velocity is not constant. So, Ethan, we'll do a crash course overview, and then if you still have questions later, you can let me know. But I at least want you to see kind of, there was a big, I guess, revelation that we had. Well, I think it was. I don't know if you guys thought it was cool. Oh, I don't want that.
Chicken broth?
Calm down, John. He legit causing me this.
So, again, you guys, I'm doing a refresher. Hey guys, can you put your phones and stuff away? Clever, but please put your phones away. So, I'm going to crash course review this to catch Ethan up and hopefully give you guys a quick refresher. This one is 5 meters per second for 10 seconds. So if we plot velocity versus time, well, any time it's just 5, so it's a straight line. The slope of that line is equal to what? It's a flat line. There's no slope. What are the units? We do rise over run. meters per second, right? Rise in meters per second, over run in second. So that's new. Where the slope of a velocity time graph, do you know what these units stick out to you? Meters per second squared? What is that? No. What was the physical term? The slope of velocity time graph tells you how the velocity changes over time. What is that? Yeah, acceleration. Right? Acceleration is how the velocity changes over time. Well, that's what the slope of a velocity time graph is. How does this line change over time? And it's meters per second. John had a good question, because later I said, okay, meters per second can also be meter per second squared. He's like, whoa, that doesn't make sense. And it was a great question. However, if we look at this, meter per second, right? It's just an improper fraction. How do we get rid of this fraction? Reciprocal, right? I need to multiply the numerator by the reciprocal of this. So this is meter per second times, there's an imaginary 1, so I put 1 over second. There it is. So that was a great question. That's proving that this is still the same as this. Right? Now, what it asks, if you look, I'm going to leave this up. What it asks you is, what's the area under this line? This was a weird question. Well, how do you find the area of a rectangle? Length times width, right? My length on this side is 5 meters per second. Area equals length times width. 5 meters per second. What's my width? 10 what? Boom. What does this give us?
15 meters per second squared.
Check the units. Meter per second times second. Meters.
Oh, right.
So why is the area under a velocity time graph a distance? And what does that mean?
Is that how far he traveled?
Yeah. It's the displacement. Meters is a distance. That's how we measure it. It's what it is. What we found out, the area underneath a velocity time graph gives you the displacement. It makes sense if you read the scenario. It went 5 meters per second for 10 seconds. Yeah, easy. Every second was 5 meters. You do that 10 times, you get 50. So the big revelation is that the area underneath a velocity time graph is the displacement of an object. Now, John, the other question we did that a lot of students miss, let me throw you this scenario. What if 5 seconds, it immediately turned around and went negative 5 meters per second? Exactly. You need to look at the area under the curve and under the curve, right? If I go 5 meters per second and then immediately turn around and go 5 meters per second, both of them were for 5 seconds long. This area, 25 meters. This area, negative 5 meters per second times 5 seconds. The total displacement is the area under the curve. In this case, they cancel each other out. It's 0. Makes sense. 5 meters per second this way, 5 meters per second that. I started and ended at the same place. That's my displacement. How would I figure out the total distance that car traveled?
You would see absolute value.
Yes, absolute value. Distance is he went 25 meters and then another 25 meters. Distance and displacement are different. Displacement is beginning to ending. That's all I care about. Distance is over that whole time period, how much did it actually move? So if you want the distance, you would do the absolute value of both of these, just add the numbers. That was kind of the big takeaway from this one. Right? Anything else that you guys want to add from that one that you remember? Okay, so if we review G, right, this one is looking at graphs of velocity. We don't have a constant velocity anymore. We got velocity in meters per second, time in seconds. 1 second, it was 2 meters per second. At 2 seconds, it was 4. 3 was 6. 4 was 8. I think I did that right. Yeah. This is our velocity time graph. Right? Those are data points. We just plot them. What it asked us is, one, the slope, and then the area under the curve. So down the slope, right, we're going to do, say, rise 8 minus 0. The run was 4 minus 0. 4 over 8 over 4. What are the units of this slope? Anybody? Yeah. Rise over run. That's the acceleration. On the previous example, it was a flat line. The slope's 0. There's no acceleration. The velocity doesn't change with time. Well, duh, it just said it went 5 meters per second the whole time. Go figure. Now, our velocity is changing. There's acceleration happening. Our velocity is changing over time. Well, just take the slope of that line, and that tells you how much it changes over time, what a slope is, and those units are every second it increases by 2 meters per second. Right? 2, 4, 6, 8. Easy. The other thing, we can still do area under the curve, which would give us what? What does that tell us? Displacement. From beginning to end, how far did it go in total? Well, how do I find the area of this? Yeah. A equals 1/2 base times height. That's the formula for the area of a triangle, a right triangle. Well, we can do that easy. What's the base? Well, 4 seconds. What's the height? Again, the height is the largest part. I don't want it here. I don't want it here. I want it for the whole area. So my height is 8 meters per second. Right? You see the seconds cancel out. Meters per second times second. Well, those are both numerator and denominator. 16 meters. Right? So I can say from this object, the total displacement was 16 meters. It's just the area under the velocity time graph. Your units will work out. You say, oh, yep, that's a distance. I did the math right. Right? So that was kind of the big, kind of, I guess, lesson learned, or the big understanding to take away. And down here, we can do a more physics-esque version of the area formula, where we say x. I prefer delta x, as in displacement. A lot of times they use X for displacement. I don't think that's accurate. X is just position. You're here. I like delta X to show this is the displacement is 1/2 the base, which was time, times the height, which was the final velocity. When we do that triangle, that height was representing the final velocity for that motion. Now sometimes it might be initial, right? It's just the height, the largest point of the triangle you're looking at. So this can be an equation, a simplified version. I would recommend, if you're doing it from a graph, just look at the graph and do it yourself. Pick up the areas. If you have a positive and negative, make sure to do those separately and subtract the two. But this would be instead of writing it as an area, we can put in the physics terms. Any other questions about that crash course review? All right. Now we're going to start putting the pieces together. We've done a lot of looking at position, looking at position time graphs. We started to see some of the connection from position to velocity. Whoops. We just saw a little bit of connection from velocity to acceleration. What we just did was displacement relation to velocity. But now we're going to formally start to put these pieces together. If I have this many.
10 paper, please.
What are you laughing at? You just threw one paper, that was it.
You're
I was talking and doing something.
like 5 forward.
I'm not good at multitasking. Oh, because we're missing 2 people.
Yeah.
I seem to misprint every time, but I got it right today, but 2 people are gone. So again, this is 1.h, relationships between position, velocity, and acceleration. So it gives you the velocity time graph. It wants you to find the equation of the line, and then write that equation not as a line but as a function with physics variables, not just y equals mx plus b. And there's a C and a D on the back in case you missed that. How do we feel about this one? No? Okay, let's go step by step. This one, we'll just start with y equals mx plus b. Right? What are the units for the slope? Yeah. What are the units for the y-intercept? Yeah, it's crossing the y-axis. That value is a meter per second. Right? What's the units for the y value? Huh? This I did wrong.
Oh, for the y value.
Yeah.
Wouldn't that just be meters per second?
Yep. Right? Our y-axis is velocity. You can check it. What's the units for t? Time. Seconds. Well, this is meters per second. Is this term meters per second? You sure? Meter per second times second. Wouldn't those cancel out and leave you meters per second? And then the y-intercept. So all the units match. So we're good. What if we replace this with, physics numbers? Our y-axis, what is the y variable? The y-axis is measuring what? Yeah, velocity. That's v. Our slope, what's the slope of a velocity time graph? Huh? Yeah, what's that quantity called in physics? The change in velocity over time. Acceleration. We're going to put x to denote it's in the x direction, which is what we got. So we could put vx. Right? The slope times what? The time, isn't it? We already did that. Right? Y equals mx. The x-axis is time. What do we replace b with? The y-intercept. It's this value. It's 12 meters per second. What is that in physics? Like in this scenario? Yeah. It's a velocity that it started with. So we're going to say vxi. Or you can put vx naught. Doesn't matter. You might see it multiple ways. This could also be vxi. Sometimes they write it vx comma I. So the I is initial. O is like original or origin. They're the same thing. The alternative, there's only one way to do it. Vx final. That's typically how you'd see it. Alright? Slope, we already said this. What's the slope representing in physics? Acceleration. I hope it's a boring, easy answer, because I want it to be like quick, like, oh, of course the slope of velocity time graphs acceleration. Now, we look at, again, these claim evidence reasonings, right? We have a claim. Car's slowing down the entire distance because the slope of the line is always negative and never changes. So let's dig into that. The car starts with an initial velocity of what? 12, right? Starts at 12 meters per second. Is it slowing down or speeding up? How do you know it's slowing down?
Because after the first second, it goes from 12 meters per second to 8 meters per second.
Great. You guys see it started at 12 meters per second. After 1 second, it's slower. It has less velocity. You could also look at, actually no, we're going to leave it at that. That's great reasoning. So it is slowing down. That happens for the first 3 seconds. What happens there?
It starts going in reverse.
The last second, is it still slowing down or is it speeding up?
It stopped and it's speeding up.
It's speeding up in the negative direction.
Bingo. This is tricky. You hit a stopping point. You're going fast and then you slow down. Eventually you hit 0 and you start going in the negative direction. So now it speeds up for the last second. A lot of students, especially when you first start doing this, you miss that. At 3 seconds, the car's motion changes from, was it initially traveling this part? Was it initially traveling in the positive or the negative direction? Positive, because its velocity is positive. It's moving in the positive direction. It switches to doing what? Now it's moving in the negative direction. That's what we just said. It's now negative velocity. That means its velocity is in this direction, our negative x direction. That intercept, this is hard. You got to look at the whole thing together. The blank when the blank of the car is equal to blank.
The time, the acceleration of the car is 0.
I would disagree with that. The slope of a velocity time graph is the acceleration, and the slope is the same all the way through. So I would say its acceleration is the same. So it's not quite that. Yeah, we hit a 0 point. What is that 0?
Oh, it's velocity.
0 velocity. So it's the time, right? At some point in time when the velocity is 0. I don't really like this phrasing because you have to guess all 3 together to get it. So I don't like how that's set up, so don't worry about that. That's like kind of a guess and check, not a, if I know physics, I'll understand that, so I don't like that. The car accelerates constantly. What's the magnitude? Magnitude.
Negative 4.
Is it 4 because magnitude is absolute value?
Yes. So I'm not trying to be tricky. It's just when, especially in science and physics, like the words we use, they have specific meanings. So this technically is just 4. It's not negative 4. Ethan's right. The acceleration is negative 4. Acceleration is a vector. The magnitude is 4. The direction, the negative sign, makes it a vector. If it just asked what the magnitude was, I'm just going to say 4. It's only the size. Why is that? Yeah, because the slope never changes. All right? Now, this is where we start to mix them up. We had velocity time. We know the slope is the acceleration. Well, let's draw a corresponding acceleration time graph. Right? So I'm gonna draw one VT. We're gonna compare them. So if I go to the back side, I now want to make an acceleration time graph of the same motion. How do I plot the acceleration of that object over time? What was the acceleration initially? Huh? Acceleration. Acceleration is the slope of the velocity time graph, right?
Nothing.
What's the slope at the first part? Not a trick question.
Like right at the very beginning?
Yeah.
It's zero.
No. It's something.
Oh.
Constant.
It's
-4, right? What about halfway through? What's the slope halfway through?
-4.
How about at the very end?
Oh, okay.
Aha! This can get hard because it's saying this is velocity time for motion. Okay, tell me what the acceleration time was for the same thing. You have to remember, the slope of this line tells me my acceleration. I can find that. I also know it's a straight line. Slope of a straight line is just a number. It's going to be the same all the way through. Here's the real kicker. Let's try to make the position time graph. We know the velocity versus time and the acceleration versus time. What about the actual position of that object over time? It's the same thing happening. We're looking at just a different variable. Can we figure this out just from these two here? It gives you a hint. It will pass through the two dots. Well, let's try something. What if I guess, I think it's like this.
It slows down. If you did that, you would be moving at the same speed the whole time.
Yes. The slope of a position time graph tells you how the position changes with time. It tells you meter per second. That's velocity. Well, if my velocity changes by the same amount, that means it's a constant velocity. Well, I definitely don't have a constant velocity. So I know my object's position time, it did not look like this. That doesn't work. What else can we draw? What do you think this point indicates? I think it was 4.
Oh, that point is when the velocity is zero.
What do we think of Ethan's claim? He said he thinks this point is when the velocity was 0. Ethan, do you have any evidence to support that?
Because the time is the same. 3 seconds, 3 seconds.
I like that. That's good evidence. All these are the same exact motion. Exact same thing, exact same amount of time. We're measuring different quantities. They're both happening at the exact same time. So these 2 points are describing the same moment in time. So Ethan and I would agree. We know this is when the velocity hits 0. That's when it stops temporarily. It's when it switches from moving forward to starting to go back. There's a brief moment in time where it stopped, and then it starts going in the negative direction. That's what happens right here. If we know that, how do we show that on the position time graph? We just said it's moving in the positive direction, isn't it? We got positive velocities, but it slows down, it slows down, it slows down, eventually stops. Doesn't it start retracing its steps? It goes back in the same direction. Well, wouldn't that mean like before and after it crosses the same point, the same position? Right? Because I'm moving forward, I stop, and I move back. At these 2 points in time, I'm at the exact same physical position, right? I move forward, I pass this point, I stop, and then I come back, cross that exact same point again. Are we going to have some sort of curve? Right? When we start, are we moving fast or slow? So every second, aren't we covering a lot of ground?
Yeah.
So this guy, this is going to be steep. But I'm slowing down. I'm covering less distance over time. I stop, and then I start to pick back up again. You see that? This is kind of the hardest one to figure out because you're kind of skipping a step, right? What does the slope of position time tell us? What physical quantity does the slope of position time tell us? Not quite. Rise over run. The slope here, how steep that is the rise over run. Meters per second.
Oh, velocity.
Yeah.
Right.
So right here, it's really steep. The position is changing a lot over time. That's a high velocity. Over here, my slope, I'm not really covering as much ground every second, right? I'm only going from, like 11 to 15? No, 16. How are the anchor pen? Oh, this is 15. Right? In 1 second, here to here, I cover almost 12 meters in 1 second. But in this second, I'm only going from like 12 to 15. I only cover 3. I'm moving a lot slower. Eventually, I stop, and then I start to pick up speed again. The slope of position time is velocity. The slope of velocity is acceleration. You see that? Am I boring you, or do you sort of get it? I need some feedback. Sort of? How about let's try going the other way. What happens if my position looks like this? We're making up our own scenario now. This is the position of my object. Let's plot velocity versus time. Huh? Well, let's see if that's true or not. How do we figure out what the velocity is over time if we know the position versus time?
Isn't that just your slope for velocity?
We want to know meters per second.
And that is meters.
Meters per second. Velocity is how your position changes with time. If you're moving fast, you cover a lot of ground every second.
So you're just constantly moving at 6 meters per second.
Yeah, right? 18 minus 0. It rose 18 in 3 seconds. Right? So it's like this. It's a straight line. Right? 6, right? Does that make sense? Well, what about the acceleration?
You're not accelerating.
How do you know that?
Because your velocity is...
Keep going. You're close.
It's not... Acceleration is meters over second squared, and our velocity isn't changing. So it's just going to constantly stay at that speed.
Yeah. And acceleration tells us how the velocity changes over time. It's not changing over time. It's literally staying the same all the time. So at any given time, I'm not accelerating. You could also have told me, well, the slope of the velocity time graph is 0.
Oh, that's what I was trying to say.
Which means that the change in velocity over time is 0.
Yeah.
That's exactly the same thing as saying the acceleration of the object 0. Right?
Yep.
Does that make sense? It'll be really important to be able to connect the dots between, they might give you, say, a velocity time graph and say, what would the position of this object look like over time? You get this, you have to show me this. They'll tell you it starts at rest, show the position time. Well, if it starts at rest, you know it starts here. Every second you go 6 meters. 6, 12, 18. Then I just connect my dots, boom. I figured out the position time graph by only knowing the velocity time graph. It's important to be able to see the connections between these. Any other questions? The next one is basically adding what we're doing, but with 2 objects in motion, not just one. Didn't skip you this time.
Don't skip anybody else.
I'll try not to. No, I didn't. I was going to say. Now we're looking at 1I. 1.I, the chase. So somebody got in trouble with the law in this scenario. Are you critiquing the picture?
Yeah. Top part is just like halfway.
You can see the rest of the tree, but not the rest.
Well, its invisibility cloak ends right here.
Ah, of course.
No, yeah, it ends here. Of course, that's the obvious explanation.
Right, yeah.
Did you know there's a company that's working on this big cloak?
Really?
They're close.
Is it using a rear-facing camera to project?
No, it bends all around.
Oh, really? That's cool.
Whoa.
Have you seen, I don't know if this is going to be it. Yeah.
Oh, yeah.
You seen this one?
Yeah. Or it's just got the camera in its.
Alright, I'm throwing you guys way off topic, but this is sweet. This is a potential invisibility cloak. This is a Mission Impossible movie. They throw up a projector screen, like it's a flexible TV.
Yeah.
And what they do is the camera faces backwards and shows you what would be behind the wall and puts that on the screen. So when someone looks the other way, all they see is what they would look at the end of the wall. So this is like how they sneak in here. So when he shows up, they stop, and the camera is in line with his eyes. So the camera is looking where his eyes would see the back wall. The camera sees that and just shows it on the screen.
That's insane.
Yeah.
You've never seen that? Isn't that from Ghost Protocol?
I think it is.
And they end up
Yeah, it is.
blowing up the.
Yeah, there's a scene where he steps in front of the camera, and so the screen is showing like his face right here.
Yeah, I think it's that. It's this scene. It's just later in it.
Yeah, he almost messes it up.
and then later, like more than one person comes out and it can't like show all of
Yeah,
their
yeah.
perspectives.
I think it's right here. See, that's the camera. I hope it shows it soon. Yeah, right here. He's right in front of the camera. So he almost blew their cover. Anyway, totally distracted you guys.
I like it. This man's going like 11.1 mile or meters per second over the speed limit.
He's probably out there on Rockwood.
Oh yeah.
That's what all the cool kids do that. Including John's brother.
It's kind of hard not to speed in that area.
Yeah.
I mean, it switches from 40 to 30.
Police officer has to catch up to him. He's speeding too in the school zone. So
He
now
is.
there's twice as much danger.
Then you get the citizen see the cop speeding and he chases him down to give him a citizen's arrest.
So then
Another cop shows up, sees that citizen chasing the police,
Yeah, it's
and speeds up to give him a
so
ticket.
It's a paradox.
And then another citizen.
So the paradox.
We just made we just made a fractal of people chasing each other.
Yeah.
A fractal of police speeding tickets.
Therefore, I think there's no need to answer. The answer is fractal.
The answer
It's fractal.
is
42.
Oh, you're right.
42. 42.
Times infinity.
Alright, so 42.
42 seconds.
How about 42 infinities?
Oh, you're right. You're right. Or 42 to the infinity power. How about that?
Okay, so since we don't have a lot of time, right, we get out at 40, don't we? 45?
Next class starts at
Next one starts.
Yeah, you're right.
You're supposed to go and make sure that the
Thanks, Aiden.
Yeah, no problem.
All right. So when we plot this,
Please don't actually just be a smart car. That's why you can't see the whole thing.
how big is that tree?
Have you ever seen how big a smart car is?
Yeah.
It's literally the front end.
Well, police-
and a
you
front
you
car.
can perpendicularly park in a parallel park spot with a smart car.
That's true.
So instead of like pulling in a parallel parking spot, I can literally pull straight in and park.
See,
'Cause they're
that's
so
why-
short.
That's why it's completely possible.
Their length is the width of a car.
Well, and
Yeah,
then
it's a smart
also,
car.
the
It's
Chevy
almost
Sparks are pretty small too, but I don't know if they're as, but they're not as small. I don't think.
Right, I don't think so.
They still look pretty ridiculous. It's a sample car.
So this one's a little tricky, right? We can plot the truck's motion easy, can't we? The truck's 20 meters per second the whole time. Right? How about the cop? What is his velocity time graph? Shame on me. Look like for the cop?
For the first 5 seconds, he's not moving, and then he starts gaining speed at 2 meters per second.
Right? He's at a dead stop for 5 seconds. If he goes 2 meters, his speed increases 2 meters per second every second. How much did it increase in 5 seconds?
10 meters.
10. How about in another 5 seconds? It's another 10. Right?
But it never says that the truck actually, the car actually stops the truck, does it?
No, that's
So-
what we need to figure out.
So does the cop car just keep going way past him, and then
Well, he's not.
he just drag races?
He's not with the truck at that point.
No, but what I'm saying is, it doesn't say he ever stopped the truck. He just said he caught up with the truck.
That's what you got. Oh,
So he's just.
we got to figure out Does this make sense? The time when the speed of the car, the speed of the cop car and the truck are the same, obviously, when they're at the same velocity, that's the time that we would mark. Okay, how will the positions of the car compare when they're going the same speed?
The truck is going to be way ahead of them.
What do we think about that? They're going the same speed at this time. Are they in the same position?
No,
Ethan says no.
not even close.
What do other people think?
I think Ethan's probably wrong.
What? Thought you were going to
How do we figure out position from a velocity time graph? We did it at the beginning of class.
At that point,
We do the position time graph.
Well,
meters
yes,
per second.
we can do it easy. We can do it right on here.
It is meters per second.
Can we tell how far one of these vehicles has gone
Yes.
from a velocity time graph?
No.
Yes, how? We can.
Oh,
The area or something like that.
Yep. Area under the curve. The displacement.
right.
So I find the area, that's meters per second times second, that gives me meters. That's how far this cop car has displaced from start to end.
Halfway there.
Ethan is right. How do we know Ethan's right? No, that's a terrible answer. No offense to you. In science class, that's a terrible, terrible answer.
But if you know Ethan, that's a fairly
Not in science. Albert Einstein could have given that answer, and if you gave me that reason, well, it's Albert Einstein, I'd say no. I wouldn't agree with that. Not in science.
And then I'd say, tell me why.
Tell me why? Because he has no evidence to support his claim.
He has all the evidence on his paper.
What is that evidence? That's what we care about.
You're like referencing a reference is what you're doing.
Okay,
No.
wait, I got this.
I'm saying that evidence does not support the claim. There's no connection, so I throw that evidence out.
I got this.
No evidence has been given other than because he's Ethan.
Yeah.
That evidence I dismiss.
Right.
Because Ethan.
Because
What evidence supports the claim that the truck is at a much further position than the cop car,
Because
even though they're going the same
the
speed?
cop car wasn't moving for the first 5 seconds.
Kind of. But
It was just vibing.
if the truck was moving at 5 meters per second, the cop car still wouldn't have gone for the first 5 seconds. It probably would have caught up by then.
Yeah.
How do we know the truck has displaced more than the cop car?
Because the cop car wasn't at a constant velocity of 20 meters per second.
The area of that one is 300. The area of the other one is 270. No, 120. 100.
Like we'll have to wait till.
Otherwise, you can see this. The displacement at this point in time of the truck is the area under the curve. That's a big area. The displacement of the cop car, it's only this little sliver. We know this truck has displaced much further than the cop car at that time, even though they're going the same speed. All right, I'm running out of time. I'm going to give you guys some homework.
Whoa, bro, not cool.
Dude, I haven't had.
No, it's going to be totally cool.
Calm down.
Let's have some money.
So the homework I'm giving is 1J and 1K. I'm going to challenge you guys to try and do this. All right? 1J and 1K is your homework. Get as far as you can.
I get it, we don't actually have to do it because it's JK.
That's actually really fun. Sorry I didn't get this out before the bell rang.
It's fine. It's not like we have anywhere important to go.
And sorry I squandered like 15 minutes of your day.
It's Indian success.
And all I did was show you.
15 minutes. This will only take me about an hour at least.
But have you heard that Elon Musk wants to shoot a movie in space with Tom Cruise?
Is that true?
I think so.
Wait, what's going on?
Elon Musk wants to shoot a movie in space with Tom Cruise.
All right, have a good weekend, you guys.
Actually,